Hi all. So here we have addressed a major issue, a major disorder called as autonomic dysreflexia. So this issue is such that we know that most of the spinal injuries are a common thing that we can see. Around 40 to 50% of the people often have spinal injuries, which as a result causes huge problems in their muscle activity and further the entire nervous system, and therefore causing a stroke nearby. So here we have built a wearable device, a wearable leg device. So this is the device we have built, and we have named it as AYRA.
So this is single unit wearable device, and we use edge processing. So nothing is sent to the cloud, and the personal data of the user is stored locally and only accessible to the user.
To start off with what autonomic dysreflexia is, it's a disorder that often causes about T6, T7 level of our vertebrae system. So in this requires a lot of processing, such as we have to look into the blood pressure, vasoconstriction, our conductance of the cell, and etc. activities. So to start off with the sensors that we have used in this wearable device. So the first sensor that we have used is a PPG heart rate system. So we have to understand the blood pressure rate in order to understand the vasoconstriction level, and the best placement of that is below the leg level. And the second sensor that we have, second thing we have used is a GSR electrode system. So we know that skin conductance occurs, and skin conductance occurs which in the sympathetic nervous system, which often measures the pseudomotor activity. So for that, it's a fight response that we have understood through GSR electrodes. So that is also the next parameter that we have to look into.
Here we use the parametric sensor provided by the Myosa kit, which we are using to calibrate the atmospheric pressure. So when we're measuring humidity and temperature, we can use that to correlate to the atmospheric pressure and see if the data reading is right. Then we use the accelerometer and gyroscope sensor. So apart from the usual movement, if we have any jerk movements which is abnormal and it is out of the pattern, we use the pre-trained model we have here, and we are using the data set from the International Spinal Society, and we got a data set for that, and we are using a DNN architecture, which is a deep neural network, specifically the 5 deep neural network architecture, and that provides usually a 94.7 to a 97.8 accuracy. So if we have any abnormal moments, we'll be able to detect it pretty quickly. We have the OLED screen connected to our Myosa ESP32, and our OLED screen here just shows the model prediction and the inference that happens. Okay, and the rest of the data is sent to your phone. And so we have we have it hosted here. So the project is called AYRA, and here we can see the AI prediction model, and we can see the accuracy score, as in how confident the model is. See the model confidence score, and here right now it's 90.3. But if it starts moving, or if if there's any change in humidity, or if AD actually starts to happen, we can see the heart rate variability. Right now is pretty normal because he's not actually suffering AD. And skin conductance. Skin conductance is what Sheila explained earlier, and temperature fluctuation and spasm activity by the accelerometer and gyroscope from the usual movement. So if he's walking, we can differentiate that from spasms.
So understanding the pseudomotor activity, the vasoconstriction, the blood pressure levels, the temperature references, we can have a detection. We can have almost an understanding of if AD is present. We are predicting it. So this prediction system always helps in better prevention of it, and also curing and finding a faster relief method.
So right now we can see the AD risk is low, and the pressure is this much, and all the readings are written here. For full transparency, this is the heart rate monitor, so we can see the heart rate here. None of this is hard coded. Everything is streamed real time from our ESP32. Show you the edge processing. Okay, this is edge. We use INT8 quantization, which is perfect to run in ESP32. So running TinyML is hard, so INT8 quantization is the best possible outcome, and it runs on 42 KB of memory and around 8 milliseconds. And this is a data pipeline, and spasms, you can clearly see the spasms here. Right now it's pretty normal and he's not walking. And the pressure sensor, atmospheric pressure sensor, and heart rate. So this is the heart rate sensor, go down, and this is the entire setup. So we'll have a patch here. This is just a MVP. So we can actually kind of clean it up and 3D print the box and the rest of the system. And we can use a belt here to hold all the sensors. And these are the skin conductance sensors. The Myosa board is right here. The OLED sensors showing the inference, and it will also show the risk level, which is also streamed on your phone. So, this is a project. Matthew, she will add on an away from Savatya Engineering. Thank you.